Okay, recording has started. So good morning, everybody, and welcome back to Math 115. So today we're going to continue on with our review. So for those of you that are still here with me in person, how are we doing today? Happy 420. No, we don't say that. Not in this state. This state it's still very illegal, I think. But yeah, you're right. It's April 20th. How's everyone else doing? Surviving out there? Tired, yeah, me too. I'm really tired this morning as well. Sleep deprived. Otherwise okay, though? Okay, good. All right. Well, what we're going to do today is just kind of carry on with this review. So as I said last time, I think that the students who get the most out of this review are going to be those who go on the blackboard, download this exam, try the problems, and then come to class and, have questions ready and have some amount of foreknowledge of what they know and don't know so that they, know which parts of the review that they need to pay special attention to and which parts they have down pat. So that's my guide for how to make the best use of this review. So last time we talked about these true and false questions. We went through all of those. So those reviewed us about some basic cancellation of rational expressions, inverse functions, what it means for a set of ordered pairs or for a relation to be a function. Remember, that had to do with no repeated x values, well, if there are no repeated x values, or if it passes the vertical line test, then the set is a function. So we could come up with a set of ordered pairs which did not satisfy those criterion, and therefore it wasn't a function, and so that was a false. So we reviewed what it means for the graph of a function to have a horizontal asymptote. And we had a basic question here on a transformation of a sine function. And so that was just about understanding how do these transformations affect the period, which if we shrink the graph, so too shrinks the period, right? Okay. Oh, and I guess there was another problem in here, which I didn't even see because of all this other work we did. We were supposed to find the distance and midpoint between -1, 2 and 3, 1, -1. We'll do that in a minute. But I do want to advertise first that after class, I went through a ton of examples about linear equations. Okay, so I just want everybody to be aware that there's some recorded office hours from after class yesterday. I went through what is a line, what is a linear equation, what are the ways which we see linear equations, like slope-intercept form, point-slope form, standard form. And I did, what is slope, what is a y-intercept, and I did a ton of examples of different lines and how to graph these lines and how to do some of these problems where you got to find the equation of the line that passes through these points and so on and so forth. And as well, I talked about parallel lines and perpendicular lines. So everything about lines is basically in the last lecture. So if you want to have a very comprehensive review of lines, go check that office hour session out. Okay, but for now, I'll copy this question down. So distance and midpoint for -1, 2, and 3, -1. And we'll do that one real quick before we move on. page. So it was distance and midpoint for 3 and -1. What was the other one? -1, 2. Okay, so of course, if you remember the distance formula and the midpoint formula, then you can just go ahead and knock this problem out really quickly. So I'll show you how to do that, and then I'll show you how to do this if you forget. So using formulas, the distance formula is the square root of y2 minus y1 squared plus x2 minus x1 squared. So for us, this would be equal to the square root of, well, the y2 is going to be this one, and then y1 will be this one, and then x2 will be this one, right? The x-coordinate of the second point, and then the x1 will be the x-coordinate of the first point. Okay, so if we just plug those all in, we'd get -1 minus 2 is -3 squared is 9 plus, well, x2 is 3, so we take 3 minus 1, -1 is 4. Square that, we get 16. And then this is going to be the square root of 25. So these points are exactly 5 units apart. Then the midpoint can be found using the formula x2 minus x1 over 2. Wait, no, it should be x2 plus x1 over 2, sorry. And then the other one is y2 plus y1 over 2. Okay, and this one's easier to remember, I think, if you think about these as an average. This is the average of the x2 and the x1. So we just take their average, and that will be the midpoint value for the x-coordinates. Okay, so this will be exactly halfway between the two x values, right? This is like how you calculate the class average, right? If one student's score is a 70 and one student's score is 100, then the average will be exactly halfway between, right? At like, I don't know, 85. Okay, so in our case, we take x1 plus x2. This time it's a plus, so -1 plus 3 is going to be 2. So 2 divided by 2 is exactly 1. And the y2 plus the y1, well, we do -1 plus 2 is 1. Divided by 2 is just 1/2. Okay, so this is the midpoint. So that's how you can use the formulas. But you can also use geometry. It's not too hard to use geometry here. So let me use a coordinate axis here. One, 2, 3, 4, 5. And I'm going to copy this so that I can use it later. Okay, so where's -1, 2? Remember, -1 tells us how far left and right. So a -1 means we go left 1, and then the +2 here means we go up 2. So left 1 and up 2. Here's our point, -1, 2. And then the other point we have is, what, 3, -1, which means we go to the right 3 and down 1. So I go to the right 3 and down 1. Here's my point, 3, -1. And if I want to find the distance between them, so this red line here is what we want to know. We can use the Pythagorean theorem by setting up a triangle. Well, I know to go down from -1 to from 2 to -1 in terms of my y values, right? I know that this distance that goes from 2 to -1 in terms of the y value should be 3. And I know that the distance which goes from -1 to 3 in terms of the x values should be 4, just by counting the tick marks, right? And then if I have a 3 and a 4 and I have a right triangle, well, this has to be a 3, 4, 5 triangle, right? It's a Pythagorean triple. Okay, and then as far as finding the midpoint, okay, we just cut each of these in half. So if we cut 4 in half, that means we go 2. And if we cut 3 in half, that means we go 1.5. So 1.5 down from 2 is exactly at the point 1/2 here. And then this would be the point 1. Okay, so the midpoint is right here at 1, 1/2. So that's how we can use geometry instead. So if you forget the formulas, it's no big deal. Of course, on the exam, you're going to have open book, open notes. So all you have to do if you want to remember what the formulas are go open the book, go to the index, and find wherever it says distance, go to the page that it says the distance formula is on, and then you're there. Or you can go back through our notes if you want. Okay, pretty simple problem. Any questions about the distance and midpoint problem? I bet distance and midpoint is something you'd love to see on the exam, right? All right, if no questions, we will move on. So in the last class, we did this problem about, I keep adding pages there. I mean to add pages here. Last class, we did this problem about finding the equation of the line which is parallel to 2x plus 3 is equal to 4, and containing the point -3, 0. Okay, the way we did that was by rearranging this line, which was in standard form, into slope-intercept form so that we could figure out what the slope of that line was. And then we knew that line 2 should then have the same slope as our other line because it's a parallel line. And it should also pass through the point -3, 0. So once you have those two pieces of information, you can go to one of two routes. You can take Justin's route, which is to take y equals mx plus b, plug in the slope, and then take -3, 0 and solve for b by putting -3 in for x and putting in 0 for y. Once you get b, then you can just go back to your old y equals -2/3 x plus b and replace b by whatever you solved for b to b. So that's one method. The other method is to use point slope form, which point slope form of a line, remember, is y minus y naught equals m times x minus x naught. Okay, where x naught, y naught is the point on the line that you have, and m is the slope. So if we just plug in these values of -3, 0 for the x naught and the y naught, and then -2/3 for the m, then you can see that down here, I did that after class. It's just y minus 0 is equal to -2/3 times x plus 3. And if you actually multiply this out and distribute that -2/3, you get the same exact thing as you see right here, okay? These are the same. Just written in a slightly different way. Okay, so that's another way to do it. So I promised that we would also cover how to find the perpendicular line. Okay, so I'll go through that now. So we have the equation 2x, what was it, plus 3y is equal to 4. and it goes through -3, 0. So perpendicular to. Trying to find the equation of a line that is perpendicular to the line 2x plus 3y = 4 and goes through the points -3, 0. So as usual, I think that the fastest way to do this is first to get our hands on the slope of this line, because we know the slope of the perpendicular line is going to have something to do with the slope of our original line. Okay, so the slope of our original line, remember we did that, it was just, we rearranged this equation, we added 2x, or subtracted 2x over to the other side, divide by 3, and we get -2/3 x plus 4/3. Is that what I even did last time? I forgot to even divide both this by 3. Didn't really matter, right? Because that y-intercept didn't matter. Okay, so we have this line now, and we know that the slope of the original line is -2/3. Okay, so perpendicular, just let's recall what that means. Perpendicular means the lines cross and form a right angle. Okay, so visually, what does this look like? If we have a coordinate plane, it looks like the following. If we have, line number 1 here, maybe it looks like this, and line number 2 is exactly perpendicular by forming a right angle on the points where they cross. Can anybody tell me what is the condition on the slope of the second line? So let's call the second line line 2, and this is line 1. And we know that m1, the slope of line 1, is m1 equals -2/3. How do we find the slope of line 2, which is perpendicular to line 1? Can anyone tell me how we find this slope? Very good, Catherine. Negative reciprocal. Okay. The equation, or the slope of a line which is perpendicular to line 1 will have slope which is equal to -1/m1. Okay, so all we have to do is plug in. We get -1 divided by -2/3. Dividing by a fraction is the same as multiplying by the reciprocal, so we get -1 times 3 over -2. The negatives cancel, and we wind up with just 3/2. Okay, 3/2. So the slope of line 2 should be 3/2. Now, remember, a perpendicular line is just a line which satisfies the property about the slope of this line. Okay, so if I take this line, which is perpendicular to my original line, and I move it over, it's still perpendicular. It is still perpendicular, and it's still perpendicular. So it doesn't matter what the y-intercept of our line is. The only thing that matters is that it has a certain kind of slope. So we need to satisfy this property of the slope. But as for what the y-intercept is, it doesn't really matter. Oh, yeah, it does. Sorry, because it's supposed to pass through the line -3, 0. Sorry about that. So any line will be perpendicular if it has this slope, but there will only be one line which goes through the point -3, 0 and is also perpendicular. Okay, so we also need this line here to go through the point -3, 0. So if we mark it, here's -3, 0. It has to go through that point, so we know we have to move it over to the point where it goes through that line right there. Okay? So that's the equation of that line which we need. It should have slope. God, of course I didn't even draw this right. All right, I'll draw it right. -2/3 x plus 4/3 looks something like 4/3 looks something like this. And then our line will be the one that goes through that and is perpendicular to it. So this is line 1, and this is line 2. Right, has slope 3 halves. And goes through the point -3, 0. Okay, so we have the slope and we have the point, so let's go ahead and use point slope, right? We got y minus y naught equals m times x minus x naught. Well, I know y naught is 0. That came from the fact that the point -3, 0 has 0 for the y value. And then I'll have m should be my new slope, 3 halves, times x minus, what is the x value of this point? It's -3, x minus -3. So in other words, y is equal to 3 halves times x plus 3. Or if you want to multiply it out, then it's y is equal to 3 halves x plus 9 halves. Okay, so that's one way we can do this perpendicular line. Any questions about perpendicular lines? All right, I think the most important thing to remember is that if two lines are perpendicular, then the slopes of the line satisfy this property, that each slope is the negative reciprocal of the other one. Okay, that's what perpendicular lines do. Okay. Next question. We're not going to do the oblique asymptotes. We didn't learn how to do obliques. But we're going to find all asymptotes of this function, vertical and horizontal. So remember that an asymptote is a line. A line which the graph of this function is going to get closer and closer and closer and closer to. So, for example, a horizontal asymptote looks something like this. It's a horizontal line such that the graph of our function f of x gets really, really close to this line in some direction, maybe in that direction or maybe even in this direction. We don't know. Okay, so that's a horizontal asymptote. And then what does a vertical asymptote look like? Well, same deal, except it's a vertical line. So a vertical asymptote looks like a vertical line. Vertical, see. Okay, and then the graph of our function f of x looks maybe something like, I don't know, this. Getting very, very close to, but never touching. Okay, so those are the vertical and horizontal asymptotes. And remember, what we said about vertical asymptotes and horizontal asymptotes is that the vertical asymptotes, okay, are really the ones where the value of the function is like blowing up, okay? Something really bad is happening to the function at a vertical asymptote because the value of the function, the height of the function, is going to infinity or to negative infinity. Okay, so it could also be going down like this, right? Okay, so when is that going to happen? When are we going to have a vertical asymptote when our function is defined by a rational expression? Whenever, can someone fill in the blank here of when we're going to have a vertical asymptote? Totally forgot how to do these. It's good that we're reviewing then. Well, if we have a fraction of one number divided by another number, what condition might make this go to infinity? What do you know that makes a function really blow up like crazy? Very good, Heidi. When the denominator, I won't say that, yeah, has a vertical asymptote, I guess wherever, maybe I should say wherever. The denominator is going to be going to 0, right? Of course, there's a small caveat for that, which is that the numerator should also not be 0. Because if the numerator is 0 and the denominator is 0, then we have some other kind of behavior. Can someone tell me what kind of behavior we have when the numerator and the denominator are both 0? Very good, Sam. We're going to have a whole if the numerator and the denominator are both 0. So we need the numerator not 0 and the denominator going to 0. Okay, so we want to check when is d of x equal to 0, the denominator is equal to 0, but n of x is not equal to 0. So when is the numerator 0, or the denominator 0 and the numerator not 0? Well, the denominator is 0 when x is equal to plus or minus 3. Right? If I plug in 3 squared or negative 3 squared. And I can see that the numerator is definitely not going to be 0 for those values of x, because if I plug in 3, I'd get 4 minus 36. And then if I plugged in negative 3, I'd get 4 minus 36. And neither of those are 0. So we're going to have a vertical asymptote at x equals 3 and x equals negative 3. Okay. Now, horizontal asymptotes was a bit of a different situation. What did we need to look at in order to determine whether a rational function had a horizontal asymptote or not? Does anyone remember what we had to look at to check whether these functions would have a horizontal asymptote or not? Very good, Sam. We need to look at the degree. Okay, so just to remind everyone what that word means, the degree is the highest power of x, which is present in a polynomial. So if we just consider the polynomial n of x, which is 4 minus 4x squared, then n of x has degree 2, because the largest power of x, which is present in that polynomial, is x to the power 2. Okay, so we got to look at the degree of n of x and d of x, and then we're going to have different situations with our horizontal asymptotes depending on whether the numerator has higher degree or the denominator has higher degree, or if they have the same degree. Okay, so the reason we want to care about the degree of n of x and d of x is because when we have one of these horizontal asymptotes, what we're saying is that when x gets really, 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 really big, then the function value is getting close to some number, right? Or when x gets really, really, really big in a negative way. When x is extremely large in absolute value, 4x squared will be like way freaking bigger than just the number 4. So this is somehow to say that when x is extremely large, the only term that matters is going to be this one, because this is going to be like the number 4 billion, or 4 minus 4 billion is just really, really close to negative 4 billion, right? So the only one that actually is carrying all of the weight of the numerator is going to be that term with the highest degree. And likewise, if I had a 4x here, I mean 4x squared is going to weigh out 4x by a lot in the long run. So that's what we care about most, is just the term with the highest power. Okay, so if we had 3 cases, if n of x, no, if degree of n of x is larger than degree of d of x. So the numerator has higher degree than the denominator. So maybe the numerator is something like something, something, something x to the 5th, and then the denominator would be something, something, something x to the 3rd. Okay, if the power is higher on top, no horizontal asymptote. If the degree of d of x is larger, than the horizontal asymptote, because the degrees are equal. We're almost there. So no horizontal asymptote if the numerator is larger, because then the numerator will just outweigh the denominator ultimately, and so that will go to either like plus or minus infinity. If the degree of the denominator is larger than the numerator, then ultimately this number is going to have a really, really big number on the bottom and a smaller number on top. We're going to have a horizontal asymptote in this case. That horizontal asymptote is x equal to 0. And finally, if the degrees are equal, degree of the denominator is equal to the degree of the numerator, the horizontal asymptote is given by the ratio of the coefficients on the largest terms, on the, sorry, not the largest terms, on the leading terms of n of x and d of x. So the coefficients in this case, which are on the leading terms, are going to be, the coefficients on the leading terms are going to be, well, whatever number is out front of the leading terms. So for the numerator, the coefficient here is -4. And for the denominator, the coefficient here, well, there's no coefficient, which means that the coefficient is 1. So in our case, in this problem, let me switch color. In this problem, we have case 3. The degree of the numerator is 2. The degree of the denominator is 2. So those degrees are equal. So the horizontal asymptote will be given by the ratio of the coefficients on the square terms, because those are the highest power terms. So we look at -4 divided by 1. So we get y equals -4 divided by 1 is a horizontal asymptote. Okay, so we get a horizontal asymptote, which is really going to depend on the degree of the numerator and the denominator. Okay. Are there any questions about this problem where we found the vertical and horizontal asymptotes of this function? Okay, I think this was one of the, harder things that we did in the sort of first section of the class before we started trigonometry. I think this was one of the harder things. So if this is something that you're like, oh, I just vaguely remember doing that, but I could never possibly produce it on the exam, this might be something that you want to study and do some practice on. Okay, seems like there's no questions on that one. So take-home message, vertical asymptote is happening when the numerator is not 0 and the denominator is 0. Okay, so one thing that happened on the exam, for example, was I gave a question that was like, describe in words when a rational function will have a vertical asymptote. And a lot of people wrote, you will have a vertical asymptote whenever the denominator is equal to 0. And those students who wrote this did wind up losing some points because, well, it's not entirely true what they said. Because the denominator can be 0, and if the numerator is also 0, then we would have a hole. So that's not the best characterization that we can give for a vertical asymptote. We need the denominator equal to 0 and the numerator not equal to 0. Okay, and then horizontal asymptotes are really asking about what's happening to the function very, very far away in terms of x values. So x values which are extremely large or extremely negative. And then in those cases, the terms with the highest power are going to be what kind of dictates the behavior of the numerator and dictate the behavior of the denominator. And so we just want to look at those two terms and see, well, do they have the same power, smaller power on one or the other? And then, depending on those situations, we're going to have one of these three setups. Okay. Well, we will move on then and talk about this final function. Okay, so, or not this final function, this function. And we're supposed to find its domain. Okay, we're supposed to find its domain. Okay, now, this is not a trigonometric function. This is just one of our, typical functions from like the first portion of the class. Okay. And we had the following. For non-trig functions, we had two things to worry about. We have two things to worry about with respect to the domain. Two rules which we have to satisfy with our domain. Can someone tell me what are the two things that we need to worry about when we're thinking about the domain of a function like this, or a rational function, or a polynomial, or these sorts of things where we have powers of x and maybe some square roots thrown in and some fractions and stuff? What do we need to worry about regarding the domain of a function if it's not specified? Well, recall the domain of the function is just all values of x for which the function is defined, right? So what are the two things we want to worry about if we're maybe running into a situation where it's possible for our function to not be defined? When might our function not be defined? Someone could maybe give me one. Yeah, that's one of them. Actually, even more than no square roots, no even-powered roots. Of negative numbers. This one seems like it's going to be applicable for this function, for sure. Okay, so no even-powered roots of negative numbers. What's the other thing that we have to worry about in terms of our function not being defined? It's the most obvious case of when a function is not defined. What's the one thing we can never do in mathematics? No dividing by zero. Okay, so in our case, we have a function here which involves a square root, but no fraction. So we don't really need to worry about this one. Number one is not really applicable for this problem. But number two is definitely applicable for this problem because we do have an even-powered root here. It's a square root. So we're going to need to make sure that whatever this number is that we're taking the square root of, it definitely needs to be larger than or equal to 0 for f of x to make sense. Okay, so, well, what are we interested in saying? We're interested in saying which x values cause this function inside to be larger than or equal to 0. That would be the domain of the function. So the domain of the function is the set of x values for which f of x makes sense. And therefore, we need to find the set of x values for which this quadratic expression is larger than or equal to 0. i.e., we need to solve the inequality x squared plus x minus 12 is larger than or equal to 0. This is what we want. Okay, so ultimately, this question is asking us something about the domain of a function. But in order to find it, what do we have to do? We have to solve a quadratic inequality. We have to solve a quadratic inequality. Now, I'm going to show two methods for solving this quadratic inequality. So let me bring it down here and show you method one. Maybe someone can tell me one of the methods that we use for solving a quadratic inequality. How do we solve quadratic inequalities in general? Anyone have a method that they'd like to share? Yeah, I think finding the zeros is definitely a good first step. So if we want to find out what the zeros are, well, all we would have to do is factor this equation, which this one factors fairly easily as x minus 3 and x plus 4. Can anyone tell me what I should do from here? There's a couple options, really. Yeah, that's true, Heidi. X equals to 3 and x equals to negative 4 will be the zeros of this expression. But we're supposed to find all values of x such that if we plug them in to this function, I get something which is larger than or equal to 0. For example, x equals 5 works too. I could plug in 25 plus 5 minus 12 is definitely larger than or equal to 0. So I need to find some expression of all of the possible values for which this function is going to take a value which is larger than or equal to 0. So you're right, we would put those in interval form, right? At some point, I think our answer is definitely going to involve interval notation, right? It's definitely going to involve interval notation, but how to figure out what those intervals are is, I think, the crux of this problem. Okay, well, seems like maybe we need a refresher on this. Method one is to use a number line. Hopefully that jogs your memory. Well, if we have a number line, what do? We put on the number line the zeros of our function. So like Heidi was saying, the zeros of this function happen at 3 and at 4. Negative 4, sorry. And what we're going to do now is pick a test point from each interval. So I'll pick one like 0. That's an easy one to pick. That's in between there. I'll pick another one like negative 5, and I'll pick another one like 5, or maybe 4. Numbers which are easy to plug in. Okay, and I'm going to check each zone. Check. X equals negative 5. I plug it into the function. I'd get, well, I'm just going to plug it into the factored function. Same thing. So negative 5 minus 3 is negative 8 times negative 5 plus 4 is negative 1 equals 8. which is larger than or equal to 0. So this region is good. Okay, then I check x equals 0. I plug it into the function. I get 0 minus 3 is negative 3. Multiply that times 0 plus 4 is positive 4. I get 12, negative 12, which is less than 0. So this one fails. So this whole region is bad. Then check x equals 3. Plug it in. Not 3, sorry, x equals 4 was what we were supposed to do. Plug it in, and I get 4 minus 3 is 1, times 4 plus 4 is 8, equals 8, which is larger than or equal to 0. So check mark. This region is good again. Okay, so I figured out what are the good regions and what are the bad regions. The only thing that's left to be a little bit careful about is whether or not we have a greater than or equal to sign or a greater than sign. In this case, it's a greater than or equal to sign, so we should in fact include the values of negative 4 and 3, since those are the zeros of the function. Those are the ones that cause this to be an equality, but those are still okay. Equality is still okay. So in the end, we just want to express these intervals. Okay, so we want every number from negative infinity up to negative 4, including negative 4. So the domain would be negative infinity, comma 4 with a bracket. Right, we use a bracket to denote inclusion. Sorry, that should be negative 4. And then we go from 3 with a bracket up to infinity. Okay, so remember, method 1 using the number line, what we want to do is we plot all of the zeros, and we pick a test point from each interval. And once we have our test point, we just check whether it satisfies the inequality or not. If it does, then the region from whence this test point came will either be all good or all bad. Okay, that's a consequence of the intermediate value theorem. Okay, so that's method 1. Okay, so these number lines are still a thing, way back in the recesses of your mind. I'll show you method 2, which is a little bit slicker. Method 2 uses graphing. I want to solve x squared plus x minus 12 is greater than or equal to 0. I know this is a quadratic expression. This is a quadratic. The graph is a parabola. And since the coefficient on the square term is positive, direction of opening is up. Okay, so the direction of opening is up. So just like how Heidi was saying, we can solve for the zeros of this expression. We get x minus 3, or we can factor it, I guess, x minus 3 and x plus 4. is larger than or equal to 0. And then we can look at the graph of this function. Well, what does the graph of this function look like? It looks like a parabola opening up, and it goes through the x-axis at the points -4 and comma 0 and 3 comma 0. And we know it opens up, so it looks something like this. And in between it will be beneath, and above it will, and to the sides it will be above. So again, we can see that the good region here of where f of x, remember the height of this function, is exactly our quadratic expression. So the good regions are going to be the regions where the height of the function is above the x-axis, and the bad regions are going to be the regions where the height of the function is beneath the x-axis. So just looking at the graph of this equation and knowing that this is a parabola which opens up, since it has a positive coefficient on the square term, we can see that, again, the domain is just going to be -∞, comma 4, -4, and union 3, comma infinity. So that's a slightly slicker way of making that argument. But the test points one will always work, and the advantage of the test points method is that if you have a polynomial of a higher degree, like a cubic polynomial or a quartic polynomial, the number line method still works for those polynomials. Okay, whereas the graphing method, it sort of is relying on the fact that you know what the graph of a quadratic function looks like. It's always a parabola, right? So you can kind of use that fact to your advantage. But the graph of a quintic function or a quartic function or a cubic function may look very strange, and it's not always going to, have the same kind of shape. Okay, for example, quartic functions can look like parabolas, or quartic functions can look like W's, in which case you might find yourself in trouble. Okay, so that's method 2, which we can use just because we're aware of what the graph of a quadratic function looks like. Okay, by the way, the number line method is also used to solve rational inequalities. Okay, so those were inequalities where we had something like x plus 3 times x minus 4 divided by like x plus 5 is larger than or equal to 0. Then we had to also check on a number line, we had to put our 0 from the denominator as well. And if we had a larger than or equal to sign, then these guys on top got dots, and the guy on the bottom got an open circle. If we have a larger than or equal to sign. If we had a larger than sign, then everything gets an open circle. Okay, so this method was also used for solving rational inequalities. Of course, we don't have a rational inequality here. I just wanted to make a note of that. Okay, any questions about the domain of this function? Okay, so this is kind of a good problem because, it asks you about the domain of a function, and if you want to answer this question, you kind of need to know quite a lot about, what we've learned in this class to be able to solve this problem. You need to know first, what is the domain of a function? Okay, it's the set of x values for which this function makes sense. And then you need to know that, okay, well, for this function to make sense, the square root needs to be taking a square root of a positive number, right? And then from there, you get this inequality involving x squared plus x minus 12 is larger than or equal to 0. And then you have to solve a polynomial inequality, which is another topic from the course. So that's kind of kind of a cool problem that involves several different topics. So again, any questions on this entire problem?
Sorry, that must be me.
All right, seems like not. So we will move on, keep on chugging. Okay, everyone's favorite topic, polynomial long division. See if we can remember how to do that. I'm going to rewrite this somewhere else, so I have more space. X cubed minus 4x squared plus 2x minus 3. And we're supposed to divide out x plus 2. Okay, so let me remind us of the algorithm that we used for this. So if you want to see the algorithm really written down in great detail, you'll have to go back to our notes from this section. I did write out like the steps as like a 1, 2, 3, 4, 5 or whatever. So if you like it in that form, then that's fine. I'm just going to kind of verbally go through it. Okay. So what we want to do here is find basically the following. We want to take this number x cubed. We're going to take x cubed and divide it by the largest coefficient, or the largest, sorry, what I meant to say was we should divide it by the leading term of our divisor. Okay, if we divide those two things, we get x squared, right? X cubed divided by x is x squared. Okay, now what we're going to do is we're going to now subtract from the inside, we're going to subtract x squared times our divisor. So in our case, we subtract x squared plus 2x, sorry, x cubed plus 2x squared. And you can kind of see that this number x squared was chosen so that when we multiply it times our divisor, then the number which we get will be the number which is needed to cancel out that x cubed when we subtract it. Okay, so when we subtract this x squared in the numerator, or in the quotient, was chosen so that these x cubes would cancel. And then we would just be left with, well, negative 4x squared minus 2x squared is negative 6x squared plus 2x minus 3. So these ones just come straight down. And then we just repeat the process. So now we're going to choose the next one. Okay, so the next blank here is going to be the number such that if we multiply x times that number, we get negative 6x squared. So the blank should be negative 6x. So if I multiply x by negative 6x, so we subtract, we get negative 6x squared minus 12x. I guess this one's maybe not going to work out. Plus 2. Did I write it down right? Minus 4x squared plus 2x minus 3. Maybe this will be a remainder problem. Okay, so let's carry on here and see where we get. This number 6x, or this term 6x, was chosen so that when we subtract, these cancel. And then we just have to do 2x minus negative 12x. That gets us 14x minus 3. And now we just have to do the last thing, should be plus 14. Okay, so plus 14, and then we subtract now 14x plus 28. And we are left with, well, the 14x's cancel, and we are left with negative 31. And this is what we call our remainder. Okay. Also, this one we call our divisor, and this one we call our quotient. Okay, so we have a remainder. So the end result of dividing out this expression is as follows. X squared minus 6x plus 14 pops out. And then we have this remainder of negative 31. Okay, so negative 31 still didn't get taken care of. So all we have to do to kind of express that last little bit of this problem is to write minus 31 over x plus 2. Okay? So this is not unlike when you had to do, something like, what is 9 divided by 8? Well, it's 1 plus 1/8, right? Because 8 goes into 9 once evenly, and with a remainder 1. So equals 1 remainder 1. Right? So way back in the day in like elementary school, when you learned how to do this division stuff with remainders, you do 1 remainder 1, and then that remainder kind of goes over your original denominator, and that's how you get this stuff. So this is nothing different. We had basically, we divided this thing out, and we got x squared minus 6x plus 14 remainder negative 31. So I just wrote x squared minus 6x plus 14 minus 31 over my original divisor. This is nothing but the same thing which you're used to doing since a very long time ago. Okay, so we just have to include this final remainder term. Okay, any questions about the long division problem? Does everyone remember how to do long division perfectly well? Or do you guys think you're going to need a little bit of practice before you can make sure you have this nailed down on the exam? Israel feels pretty good about it. That's good. Anyone else? Yeah, feel good, but these are always something else. Yeah, these problems can be sort of lengthy. That's for sure. Okay.
In Indiana, one of the hospitals that I work for, They will deliver babies
So
for
this
like
one was up here.
13, 14 years old girl, but they would not give them birth control at all.
Right.
Yeah, they will be like, we can't feel this birth control.
Okay,
And
my wife's having a
I
meeting
was
right now.
a student there at the time, and I was like, what?
All right, so we'll carry on with this last problem, and I think that might be the last one we do for today. Okay, so we have a function f of x equals 4x minus 1. And what are we supposed to do? We are supposed to justify in some way that the following function is invertible, and then find its inverse. Okay, so let's dig into this a little bit. What does this invertible word mean? Well, the invertible is a term which we didn't really define in our class, so I'll define it now. It means the inverse function exists. The inverse function exists. So, my question for you all is, what condition do we know of which we can use to say that if this condition is met, then the inverse function exists? Is there a condition which we have which will tell us whether or not the inverse function exists?
It's actually, I don't know about the doctor, but pharmacists actually like this. Like,
Yeah, very good. We've got two answers coming in, both equally good. It has to be 1-to-1, or it has to pass the horizontal line test,
Yeah.
right? If it passes the horizontal line test, then it is
like,
1-to-1.
Purdue really tried to flag down those people during like interview process, and like they tried to not
All right.
get them as a student, but
Bad timing on a meeting here.
And you know, I have classmates who will be like that.
Okay, so
like,
it's 1-to-1.
Birth control prescription, and I'm just gonna toss it in the dumpster. And it's like,
If and only if 1-to-1.
I don't want to be a classmate with you.
Or, and 1-to-1-ness holds 1-to-1-ness if the horizontal line test is passed. So the way that I would answer this question on a exam is the following. I would say this is a line, and I'd draw a little graph of it. 4x minus 1 looks like this, and I would say, shouldn't use that color, I should use this color. I would say passes the horizontal line test, implies that the function is 1-to-1, implies that the function is invertible, i.e. the inverse function exists. Okay, and how do I find, if I have y is equal to 4x plus minus 1, how do I actually find its inverse? Is there a method I know to actually find the inverse here? I have a function given to me in terms of y and x. There's some process that I can use to find the inverse. Does anybody remember what it is? All right, well, we're out of time for today, so I got to give it to you before we close. It's to switch the x and y and solve for y. So in this case, this becomes x equals 4y minus 1. And I solve this by adding 1 and then dividing by 4. So I get y is equal to x plus 1 over 4. And that is f inverse of x. Okay, so inverting a function is as simple as, well, I mean, inverting the x and y. Switch the x and y and solve for y. Once we get that function in terms of x, then that is our inverse function. Okay. All right, I think we'll close there for today. Sorry for the background noise there at the end. We'll pick this up on Thursday, since tomorrow is a wellness day. Everybody have a good day and have a good wellness day. Try to improve your wellness if you can, and we will continue with this practice exam on Thursday.
Bye.
Thanks, Heidi. You too.